Okay, so in 65B, we're doing the exact same thing, but now with a base, okay, and we're titrating with a strong acid. They spiced it up a little bit by giving us different concentrations. So the first thing we're going to do is find the equivalence point. So we've got nitric acid, and it's 0.2 molar, and we've got this base, this weak base, okay, and its concentration is 0.1 molar, all right, and I've got 100 milliliters of it. All right, so that's our reaction, okay? So a before and after table have to be in moles, okay? So I know I've got this many moles. I gotta do my sig figs. This many moles of my weak base to start with. So at the equivalence point, I should have the same number of moles. Well, as you can see, this concentration is twice as much as this concentration. Therefore, I will need half as much volume. Okay? So then my concentration of my weak base, I add my two volumes together. And so my concentration is 0.067 molar. Okay? At the equivalence point, we have to do an ice table. So this guy is going to do the following. All right. So I've got 0.067 molar of this, 0 of this, 0 of this. Whoopsie doodle. Shift right. All right. We have to do our. It's a Ka, right? This is a weak acid. So I'm going to get x squared over 0.067 minus x. This x is going to be too small. My Ka, I don't have my Ka. So I have to figure out my Ka. So in this problem, I am given a Kb. So Ka times Kb is going to equal Kw. They give me the Kb as 5.6 times 10 to the negative 4th. Kw is 1 times 10 to the 4th. I mean negative 14th. Okay? So I solve for x. go. I think I did that right. And again, what is this a concentration of? That's a concentration of that. So then for my pH, I just have to take the negative log of 1.10 times 10 to the negative sixth. So my pH at the equivalence point is 5.96. Okay. So that's the pH at the equivalence point, which again we would expect, because when you titrate a strong acid with a weak base, the equivalence point will be in the acidic region. Okay. Now halfway to the equivalence point, we have to means that the number of moles is half as much. So this one is going to be so let's go back up to our original problem here. So we can still do this. Remember that at at halfway, the conjugate base is equal to the moles of weak acid. Okay? So my conjugate base happens to be C7. No, that's the other problem. The conjugate base happens to be, oh darn it, C2H5NH2. That's my weak base. The weak acid is C2H5NH3 plus. Okay? What throws some people off with the Henderson-Hasselbalch equation is that it's typically written as this. Okay? But really, what you're looking at is just that is the log of the concentration of the conjugate base over the weak acid. So don't get hung up over the charges, okay? So this one goes on top, that one goes on bottom, okay? Now, because they're equal, we know that this is going to be taking the log of 1, and the pH will be the pKa, okay? So we know the Ka, and again, this is where we label stuff. Make sure you use the Ka and not the Kb, because we have to calculate the Ka. If we go back up here, here's the Ka. They gave us the Kb, but we want to use the Ka. So we're going to plug the Ka into the problem. I forgot the power. Okay. And there's our answer. All right. Thank you very much for watching. Have a wonderful day.